Okay, let's start with section 12 and 13, the basics of topology, also basics. Yeah, I, well, yeah, that one is already in the title. So, yeah. Anyways, for a topological space, it's a collection of open sets. The sets, the members that are in the collection are called open, and they're all, it's a subset of the power set of X essentially. Could be equal, and if it's equal, it's called the discrete topology, and if it's X and phi, yeah, anyway, X and phi are in tau. So if it's equal to power set of X, it's called the discrete topology. Arbitrary unions are in there. So if for all alpha, U alpha is in tau, implies union of U alpha is in tau. And yeah, if U1 to UN belong to tau, then you finite intersections, it's closed under finite intersections essentially. Yeah. Yeah. Note that I can just define it for one intersection. So if I define it for U1 intersection U2, then it would imply the finite intersection case. Given that I can just, take it one from the collection and then intersect it with another and then another, and so nothing's really stopping me from that. So yeah, if you want to write a weaker definition, you can write the single case, the single intersection case, but the finite intersection case feels more intuitive, and then you can use it better in proofs. And yeah, I don't know why this was chosen instead of the finite one, but anyways, yeah, okay. So I'm not discussing the question part. I'll discuss that with the exercises, the list of topologies. Yeah. For the complement topology, so there's the discrete topology, which is in the entirety of the set. Of course, there has to be a X has to be a set. So there's that. So topology is described with respect to some set, any set though. Yeah. And the collection X and the empty set is also a topology, as you can see, because the unions and intersections all match up. They're contained, and this is called the indiscrete topology or the trivial topology. Yeah. And for the complement topology cases, the way to prove that they're a topology, and yeah, you have to follow the definition, is using De Morgan's law. So yeah, that's where that comes in. So using De Morgan's laws, you can prove it. And yeah, T prime containing T tau implies tau prime is finer than tau, or tau is coarser than tau prime. And if neither is the case, then they're not comparable. And if one of them is, and if it's not comparable, then it is. That's one way of defining it. Okay. Yeah. Okay. The basis. Yeah. So the definition is quite simple. It's a collection, just a collection. It will be open if we talk about the topology that's generated by it, but for now it's just a collection. And of again also a subset of power set of X. So yeah, collection of subset of X is the same thing. And for all X in X, there exists B belongs to this collection such that X belongs to B, and for all X belonging to the intersection to B1 intersection B2, where B1 and B2 are in the collection, then there exists the B3 belonging to B such that um, yeah, yeah, B3 is equal to B1 intersection B2. And hang on. Oh, it's a subset. Sorry. Yeah, subset. Yeah. And yeah, it's the containment is quite important because of the definition of open sets. From the topology generated by basis, we use the containment instead of equality quite a lot, and this can be critical because ultimately U is contained in union U alpha. Essentially, that's the motivation for the definition. So yeah, uh, that's why containment is used quite a bit and not equality, and yeah, that's the definition. And then we have the topology generated by the basis, which is a U in the topology is open if and only if is there for all members of U there exists the basis. So we have the spaces available, and B is X belongs to B, and B is a subset. So yeah, and since B is a subset of B, all such things are open. All basis elements themselves are open. But that's from this definition alone, we can prove that the basis, the open sets are the unions of these sets because the containment is already trivially verified and you can union over X. So we'll prove that. In fact, I already kind of proved it orally. Yeah. Okay. So it's trivial to verify that for all members of X, this would be the basis of the power set of X because the intersection of two basis elements is either going to be the empty set or this set, this and another basis element. And there, any open set you can think of, any subset is going to contain this. So yeah, yeah. Okay. Yeah. So it it's not quite rigorous yet, but yeah, the circles and squares they can be generalized in the once we study metric spaces or metric topologies. And in there, since this is a rectangle, we can yeah. Essentially, since rectangles can go infinitely smaller, we can get so yeah. But this will be covered more in detail when we tackle metric topologies. And essentially, we can state the bases as the distance being the same. So all sets of less than this distance. And for the rectangles, we would need a product, which we will define. But from a product, if it so essentially it's less than this distance, and then along another product, it's less than this. So if with a product, we can define a rectangle or cube or generalize. And if the distance is the same, by the ISO something property, essentially the fact that the sphere is the whatever, yeah, yeah, we're not using that. Just essentially with the same distance, you'll get a sphere or a higher dimension or whatever. But yeah, metric spaces. Then we'll okay. So yes, now we have to check that this definition is sufficient for a definition of topology. So for a definition of a topology, right? So x and phi, well, this is accuracy true. There is no member of x, so we don't need to check anything. For this one, well, it's since beta is a collection of subsets of x, for any member, you'll have to, well, for all x, actually, there exists, by definition, for all x in x, there exists a basis element. So we're done, right? That's where the first part of the definition comes in. And for the second part, we need the subset thing. So the definition of topology generated. So if U alpha are open sets and union, we have to check that the union is in the topology. So, well, let's see. Yeah. So we're taking an arbitrary member X in this, and this has to lie in some U alpha, and this is open. So there's a basis element V alpha of it. and X belongs here. But this is contained in this and contained in this. And since containment is transitive, B alpha is contained in the whole. So we've gotten a basis element, and by that definition, this is why containment was used and not intersections. And even with the intersection one, we can't use the equality thing. Yeah. Otherwise, yeah, if we define a sphere thing in the sphere analogy, if we define the intersection to also be a part of it, then we'll not get a sphere anymore. So that's one motivation. Okay. Yeah. Lastly, intersections. So the thing is, we can actually just check it for U1 intersection U2, but we don't need to. For a, actually, yeah, we'll prove it for U1 intersection U2 and then prove by induction for the finite cases. And that's exactly what I meant when I said that in the definition of topology itself, we can just use it for finite, a single intersection and prove it for general finite cases. In fact, yeah, we discussed it in finite sets too. So yeah. Well, these two are open, so there exists the B1 and B2, and the point is that there exists the B3 that's a subset of B1 intersection B2, and X is lying in the intersection. So what does that mean? That means X belongs to B3. Um, for all X, there exists such a thing. So X is in the intersection, so there exists a basis element that's containing it, and this would be a sub. This is since these two are subsets of this set, B3 is by definition a subset of by transitivity U1 intersection U2. So yeah, since U1 intersection U2 is open, the finite cases are. Yeah, you just extend the induction hypothesis. Okay. Yeah. 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 Now let's prove that another that there's another equivalent definition for stating for the topology generated by a basis. So any open the topology generated by the basis is equal to the U union beta B alpha belongs to beta essentially. That's about it. Yeah. Okay. So let's prove it. Let U be an open set in tau, right? Now, for every x in U, by definition, since it's the topology generated by the basis, this is generated by, yeah, this is the set rectangle, say it's equal to, yeah. So, hmm. So currently we're proving this direction. We'll prove the other directions. Yeah. So for all x in U tau, where there exists the basis element, x belongs to the, I'm going to call it x, yeah, subset of U tau, right? And from that union x belongs to U tau, dx is going to be equal to U tau. Why? Because it's over every element of U tau. So every element is going to belong here, right, of U tau, and it's contained for every bx, so it's going to be equal, right? Both contained in the subgroup bracket. Again, section one, we studied a lot of basic set theory. Okay, so that proves this one. Now for the other inequality or implication, however you want to look at it. Yeah. Well, yeah, topologies are closed under arbitrary unions, so we're done, essentially. Yeah. So yeah, because topologies are closed, since basis elements are already open, their unions are also going to be open. So yeah, both containments are. And that shows that both definitions are equivalent because the sets are equal, and we're defining the set here. Yeah, and so there is no method of constructing topologies. We only have a method of checking whether something we a subset of the power set of X that we've made is a topology. And for that, we just need the definition but flipped around. So yeah, for all X in U. So we have a topology already with us now this time, right? And we want to check if collection C is a basis. So for all X in U, there exists a C in C such that X belongs to C and subset of U. Yeah. Yep. And you need to show that this is a basis. So from this definition, well, for all X in U. So X is an open set, right? So for all X in X, which is the entire set, there exists well, C is by definition a subset of the power set of X by hypothesis. Yeah. So this part is trivially true. And since this part is trivially true, we got the first part of it. For the second part, well, let's see. No, not yet. Yeah. So U1 and C1, right? And U2, there exists a C2. Yeah. So took a long break, and this should give you an idea of how ahead I am. Basically, I'm actually revising until Orison's lemma. I'm going to be revising pretty much. So yeah, I'm a little ahead. Anyways, yeah. So I didn't actually fully understand what the theorem was representing. So I'll state it properly now. So a collection C is defined as essentially for all X in a set X, right? There already exists a topology that's given to us. And so we have a collection of open sets. And for every open set here, there exists a C such that X belongs to C and C is a subset of U. That's the condition for every member of the collection, right? So that's given to us. And you have to show that this is a basis, that's one thing. And then we have to show that the topology generated by the basis is the same as this topology. So in other words, it's the basis for the topology now, right? So I didn't fully understand the theorem. I thought it just means it's a basis. That was easier to prove. So I was focused on proving that. And I was wondering why the length was greater, and then I realized it. So one thing to also realize is that the topology generated as the set, U U is equal to union arbitrarily B alpha, right? This set this set is a generator of open set. It's expanding from, so it's giving us new open sets, right? That's how it's kind of working to define the new topology. And the other definition, which is where, U uh, X belongs to B belongs to U and B is belonging to B, the collection basis. Hang on, yeah. This works as an eliminator. So it checks whether a random set essentially is satisfying the condition, right? And yeah, of course, this U must belong to the power set of X. So we do have a bigger set to eliminate from. But yeah, this is eliminating from the power set of X, and this is telling us what it is. And this intuition of generator and eliminator is precisely what enables us to show that the collection, the topology generated from the collection is equal. So for the equality, we need both sides, and one side is going to be determined this way, and the other side is from this way. So that's where essentially they're collapsing on the right spot, right? So that's the intuition. That is something I can add. Now, should I skip the proof altogether? No, I'll do it at the next slide. Okay, so to show it's a basis, well, for all X belongs to X, I think, yeah, that was the statement, right? Where am I? Yeah. Yes, it's given since tau is a topology, X is an open set, so we didn't really need every open set U. We just need every open. We just need X as the open set, and a topology has that, so we're done. So because of that, we have the X belonging to C condition satisfied. Now for the C1 and C2 condition, well, we are given U1 and U2 satisfying this subset property, right? And X belonging to both of them. So I'm rewriting it. Yeah. And what now? So U1 intersection U2 is an open set, and by definition, we have a C3 that's a subset of it, and we also have X belonging to it, right? So what does that mean? That means C3 is in the collection by definition. And that means, well, by definition, C is a basis. So we're done with that, right? And because it's a basis, we have a basis that's generated by a topology. And now let's call that topology T prime, tau prime. And yeah, so let's say U is an open set in tau prime. And let's see. So which definition gives us which one, right? Okay. Okay. This contains C by definition, right? Okay. Now, yeah. So any open set that's containing every collection in it. Yeah. Okay. So by definition, every open set U here will belong here by the definition here, right? Because that's the definition of the topology generated by this thing, right? Hang on. Yeah. So I wasted a bit of time. Let's see. So yeah, I tried proving the other side, and I basically got it if this hypothesis was true, but I wasn't sure if it was. And turns out I had to read the question properly. So this is a collection of open sets. It's a collection of open sets, and by definition, that means it's a subset, right? Because every set that's open is a member of this topology, right? So yeah, I made that mistake, and then it just comes down to proving that tau prime is the smallest topology that contains calligraphic C, right? If you show that, then this is essentially implicit, since tau contains that. So if tau prime is the smallest one, then we're done. And that's essentially what it comes down to. So if W is, if any thing is an open set here, well, since this is by definition a union of every W is a union of members of calligraphic C. So yeah, and yeah, essentially W will belong to tau because tau is a topology. So yeah, so here we're defining it in an alternative way since it's the topology made from a basis and we don't know anything about that. But here we already know it contains the collection. So every possible union of C is in this tau. And because of that, tau prime is the smallest topology that contains the basis. So that's the small lemma, and that's actually in the exercises, and I'm not doing it now. But yeah, given this, from the unions we can show it. So yeah, I was stuck because of that. And that's where the wording comes in. And be careful. So that's what it means, open set. All members are open sets. But yes, after all that, we have proven that the topology, that this is indeed a basis for now, since the topology generated by this basis is the same. So yeah, I spent too long on this one. Oh well. Anyways, next one. Yeah. So this is the most important theorem I would say in this entire chapter, probably. Yeah. So tau, I don't know what happened. Yeah. Okay. Tau prime is finer than tau, and for all, yeah, for all b prime, is it prime? Yeah, for all b in So B prime here is the basis, and this is another basis. So we have two bases for this. Yeah. Hang on, have we given them or yeah, we're given them. Cool. And for all B in B prime, this there exists B prime such that hang on, no. For all X in B, there exists B prime belonging to B collection prime such that X belongs to B prime, and this is a subset of B. And essentially, if you treat B as a open set U, we get the exact same thing. And that's exactly what we're going to exploit to show that these two are equivalent. And this is the most one of the most useful theorems. So yeah. Okay. So let's go with two implies one first, right? You should know the proof always, even so. Yeah, that's why I'm trying it. Yeah. So two implies one. Yeah. So let U belongs to tau, right? It's an open set. Now, by definition, as we have a basis, x belongs for all x, take any arbitrary x belongs to U, x belongs to B, there exists B, such that x belongs to B and it's a subset of U, right? Now what? Now, yeah, now we're given this condition, so x, there exists a B prime, such that x belongs to B prime subset of U. So what does that mean? That means B prime by definition, hang on, how does it approach it? Oh yeah, all open sets are defined this way, right? So yeah, it takes, I think we also need to use the same basis theorem. So since tau contains B prime now by definition, I think, yeah, tau prime will contain it. Since, okay, yeah, so if tau contains this collection, since any set which contains it will be the smallest topology, yeah, we're done with that. So yeah, for the other one, let's see, hmm, yeah, for two, one implies two. Let's see. Yeah, so take a basis element in B, right? Now it's also an open set. So what does that mean? That means B here will be an open set here, so we can plug it in the definition that we're given. So B will act as a U, and for this U we have a basis B prime, right? That's because why is that? Let's see. Hmm, let's think. No, 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 no problem. Okay, so it behaves as an open set here, and okay, this open set belongs here, and by definition, since it's an open set, and we have a basis, yeah, okay. So we have a B prime. We are free to have this B prime, and it will be contained in this open set, right? Because every open set is here, so we're dealing with open sets here now, and every open set here will have a basis element that I should find a word for it. I think it's contained and builds it up, I guess. So this basis element builds up this B. That's the word I'll be using, I guess. So yeah, this is fine because the open set is contained here. Okay, and yeah, that's why the following are equivalent. Note that this says nothing about the containment of B and beta. We can't compare them at all because, for example, you'll find out that the topology made up of rectangles and circles for the real line are the exact same, and they can't be compared at all. That's one reason. But if this is the case, then we can get an implication for this. because this will trivially verify it since it's a basis, I think, or something like that. You can try it out. I think this follows readily from the topology being the generated by the basis being the smallest topology that contains it. So from that, it should follow readily. Yeah, and I'm not proving that lemma. Okay. So yeah, the collection of open intervals is indeed it's defined. It's used to define the basis of the standard topology. So yeah, that's how we can define it. Since all open intervals are defined, all these sets are defined, and you can diffuse these collections as the basis. So that's fine. Okay, RL. So it's defined as the basis from topology from the basis of Clopen sets essentially. I should not call them Clopen, sorry. And RK is defined as this basis, so it's already finer than the. So yeah, that lemma can be used here. It's finer than the standard topology plus these sets minus k, I believe, and k is the set 1 by n belongs to z plus. Yeah. Okay, now what? Now, um, yeah. So we need to show both of these are finer. So that's pretty simple. Let's see. So we take an open interval. Rk is already there, so since we just have that open interval, so we're fine. For this one, you take any member here. You take any member here, you can always find a closed interval here this way, like C comma D, and that's by density of real numbers or rationals. It's the same thing. So you take any x, there's going to be a real number between x and a, and there's going to be a real number between x and b. So you just choose those, right? It doesn't work in reverse because you have to include for the c, and you can't really include it by an open interval. The moment you include c, you have to exceed by something, and if you don't, well, that's wrong. So yeah, it doesn't go the other way around. So yeah, they're both finer and they're not comparable. So to show that something's not comparable to another, you have to show it's not final, and that's where the lemma comes in, the following the previous one. So it's also useful to prove that two topologies aren't comparable. For that, we use their negation. So not one is equivalent to not two. We've proven that too actually, right? So to show that tau prime is not finer than tau, what do we need? We need there exists B in the big in this topology such that um, yeah, there exists an X in B such that for all B prime in B, X is in B prime is essentially not a subset. That's how do we do that? How do we negate that statement? I guess X is not in B prime works since that automatically means that they're not a subset. So yeah, that should do it. Hmm. So if for a basis element, we have for all basis elements in the other set, such that, for this X, it's not covered. And essentially, in the case of the standard and lower limit topology, this C is that X. So there exists the C such that for all basis elements, you won't get a subset. So I'll write, oh yeah, and B prime. So yeah, this and this. Sorry, in this case, so yeah. So that's the full negation, and that's exactly what satisfies. And that's how you prove that something's not comparable. So that's also what allows us to show that they are strictly finite. So in this case, let's see, how can we not find something? Mm, it's 1 by n, right? So 0 cannot be cancelled out, I believe. Yeah. Okay, so we take the set minus 1 comma 1 minus k, right? So 0 belongs here, right? But you try to take any open interval that contains 0, it's also going to contain some 1 by n, no matter how hard you try. And that's the problem. So that's why they're both strictly finer than the standard topology and not equal. And yeah, for showing that they're not comparable, you have to do a similar argument, but to each other. So yeah, to show that they're not final, you need examples essentially, because the existential quantifier comes in. Okay, now let's see. For this A and B, what can we find? So yeah, let's take 0, comma 1. That seems the one that's most likely to cause a problem. So for 0, there is no open interval, and hmm, yeah, I guess there isn't actually. Mhm. Oh, I guess it's in the exercise now. Should I show it here? No, I'm leaving it for the exercise. It's already too much. Okay. Yeah. Now we come to the definition of the subbasis, and the subbasis is any collection such that the union of S, and I defined that earlier, is equal to S, X, and observe that we can get a basis by simply taking the finite intersections of all of them. So yeah. And why is that? Because if we take the finite intersections, we take their intersection, we're going to get a finite intersection, and it comes down to what I just discussed earlier, which is even a single paired intersection will result in a finite set of intersections. So it's the same thing. That's why, yeah. In fact, even no, that no, that's leave it. Yeah. So that's why we can define a basis this way, and yeah, since their union is X, I think X will be there, and it's going to be a topology. In fact, yeah, we have a topology from a basis itself, so we just need to check that their finite intersections is a basis, which it is. So yeah, we're done. And that covers the theory. That was too long.